Hello, everyone. My name is Umut Bulut. I'm a chemist and I work in the Faculty of Pharmacy at Acıbadem Mehmet Ali Aydınlar University in Istanbul. I will be sharing part of our results from our project where a polypeptide functionalized polymer decorated with gold nanoparticles is used as an optosensor for codeine detection, where codeine was used as an abuse drug model. I'll try to summarize these points not to exceed the 10-minute time limit. So this is my outline. I'll continue with the definition of a biosensor. This is the IPAC definition. So specific biochemical reactions mediated by isolated enzymes, immunosystems, tissues, etc. are used to detect chemical compounds by electrical, thermal, or optical signals. Now, there are a myriad of analytes that can be detected as listed here. And in this work, we analyzed a drug using an aptamer, using its aptamer via an electrochemical biosensor. According to the 2019 World Drug Report, approximately 271 million people in the world used illicit drugs in 2017, and 53.4 million of them use opioids. Pharmaceutical opioids such as codeine are easily diverted from the licit to the illicit market. Many over-the-counter painkillers and cough syrups contain codeine, and it's less regulated than some other opiates such as morphine, so getting and abusing it is relatively easy, and it's frequently abused as tolerance develops. So many people don't stop at codeine, they try to reach a better high by mixing it with other substances. So we analyzed codeine here, an opiate found in poppy plants. It's commonly utilized in the treatment of mild to moderate pain and cough. And its excessive and long-term use may be addictive, and it can even cause death. So, development of rapid, sensitive, and adaptable platforms is crucial for forensic sciences. Now, as the bioreceptor, we used an aptamer. Aptamers are single-stranded oligonucleotides that bind to target cells with high specificity and high selectivity. Their use is advantageous due to the ease of their fabrication and the lack of need to depend on cells or animals. Also, optosensors have longer shelf life, higher denaturation resistance, lower cost, and higher stability. Now, several methods have been reported for the detection of codeine besides electrochemistry, which are HPLC, GC tandem mass spec, chemiluminescence, and so on. The thing is, these methods have high sensitivity and reliability, but they require expensive instrumentation. And furthermore, sample preparation is tedious with complex analytical procedures. Whereas in contrast, electrochemical methods offer advantages like low cost, convenience, and rapid analysis. Uh, conducting polymer-based biosensors are well known. These conducting polymers are unique for biosensor applications due to their sensitivity, versatility, ease of preparation, good conductivity output, facile polymerization, and their compatibility with biological molecules. Now, this electroactive monomer is used in the study as the polymer coating. It was synthesized in previous studies from Suna Timur Research Group and used as a biosensor for the detection of cocaine. In the fabrication of the biosensor. Now, here the amino groups on the polymer backbone provide an immobilization site for the aptamer, and also the well-oriented polypeptides can improve the interaction between the aptamer and the target analyte, acting as a spacer arm. So when aptamers are used as the biorecognition molecules, the device is called an optosensor. And this is the design of our optosensor. The EBP polymer was coated, drop coated on the glassy carbon working electrode, and then cysteamine modified gold nanoparticles are immobilized via glutaraldehyde through the amino functional groups on the polymer backbone. And then, you see, they're immobilized here. And then codeine aptamers were detected on the modified surface. They were conjugated on the modified surface by affinity of their thiol groups to gold. Right? And we get a sensor response as a result. Now let's see what these responses are. So the surface modification I was talking about is first confirmed by electrochemical impedance spectroscopy. You see, here's the circuit where we have the solution resistance, double layer capacitance, charge transfer resistance. So in the Nyquist plots, we observe an increase in the RCT values. You see, as you modify the surface with polymer and then the nanoparticles and then the aptamer and then finally with codeine. So that shows the success of surface modification. And furthermore, we monitor these surface modifications and analyze binding mechanisms with cyclic voltammetry and differential pulse voltammetry. A gradual decrease is observed in anodic and cathodic peaks upon every surface modification. Because you see electron transfer between electrolytes and electrodes is hindered as the surface is coated even more, and the interactions and subsequent binding reaction between the aptamers and codeine hinders the electron transfer of the redox probe, and it causes a decrease in the electrochemical signals as you change the codeine concentration. Now, DPV is also employed to investigate the analytical performance. Seen here, the current peak decreases consecutively after each surface modification, as again the current passing through the electrode surface decreases because the thickness of the diffusion layer increases. And from these data, we plotted a calibration curve using the change in the current values in differential pulse voltammograms as a function of analyte concentration. And the linear range was found as 3.3 times 10 to the minus 4 to 33 nanomolar, which is a wide linear range for a system, and other analytical parameters such as limit of detection, standard deviation values, and coefficient of variation were also calculated. You see, we have a low limit of detection value, 3.8 times 10 to the minus 3 nanomolar. And finally, we evaluated the selectivity of the optosensor for codeine detection. Relative response signals of the interference, such as cocaine, morphine, caffeine, etc., compared to that of codeine, were assessed. And you see the results show that the proposed biosensor was highly selective to codeine. In summary, we developed a new optosensor platform for the highly sensitive and selective detection of codeine. Aptamer is immobilized on cysteamine-modified gold nanoparticles, making use of the affinity of their thiol groups towards gold surfaces. We employed electrochemical methods to investigate surface modifications and the analytical performance of the optosensor, and it provided a fast analysis. It had an outstanding analytical performance with a wide linear range and a low limit of detection. and results show that this platform is quite useful for the detection of codeine selectively, as it does not display a significant response to other possible interference compounds. So I'd like to thank to Professor Timur and Professor Yağcı and TÜBİTAK, the Scientific and Technological Research Council of Turkey, which funded the project. And thank you all for your attention.